Hi everyone, and welcome to this lesson on logic, an introduction to logic as a mathematical topic. So in mathematical logic, statements have two values. They're either true or they're false. And we'll create a space with these two values. So we have a space that has t and f, which represent true and false. And it creates a two-value system, which I think is interesting. If you're watching this video for a class, you're probably learning logic in college. Although it should, I think, be taught much earlier to students. So the system we're used to learning as children is the counting numbers, 1, 2, 3, 4, 5, and so on, which is an infinite system. And infinity is even a difficult concept for adults. And later, as you get older, you learn to add zero and negatives, and eventually irrationals, and all sorts of very complicated numbers into a very technical system. But hopefully, that will make you appreciate that we're only dealing with a system that has two values, t and f. So it sounds simple. It's not going to be quite as simple as it sounds maybe once we start doing mathematics with it, but it's in some sense a lot easier than the regular number system that you're used to. So we're going to define some logical operations on this two-point space. First is negation, and if you haven't watched the previous lesson, you should go back and watch the previous lesson to get an idea of what each of these things are, but remember that negation is to say not a statement. And negation flips the value. It's written with this little bar that goes down over here. And we would write it as the bar in front of the statement. So this is read not p. And as a formula, we can compute it on all possible values in the space, all two of them. So not true is false, and not false is true. So that's our negation operator in the space of logic. A conjunction is written with a little triangle symbol, and it's read P and Q. So if we're given two statements P, Q, and we write this symbol in between, this is P and Q. And we can compute all possible combinations of values in our space, and there would be four of them, because P could be true or false, and Q could be true or false, and then we have to consider all combinations of true and false statements, right? So a true statement and a true statement is a true statement. A true statement and a false statement is false. A false and a true is false, and a false and false is false. So if I say P and Q, that can only be true if both statements are true at the same time, right? If one of them is false or both of them are false, then that whole statement P and Q is false. For disjunctions, we have two different definitions of or, right? There's the inclusive or and the exclusive or. The inclusive or is represented by this V symbol, which is just a flipped over conjunction symbol. And that's read P or Q. So this is very important. In mathematics, mathematicians always mean inclusive or when they say or. And if we want to use an exclusive or, we'll somehow make it apparent that we mean exclusive or. So for an inclusive or, it means one or the other, or both. And in that case, all we need is something to be true for the statement to be true. So true or true is true. True or false is true. False or true is true. But if both statements are false, false or false, we get false. The exclusive or is written as a plus sign with a circle around it. So that's the symbol here. There's a good reason it looks like a plus sign, which we'll probably get onto later. But for now, let's just look at what this means. So P exclusive or Q is read with an exclusive or, so we have to make it completely apparent that this means exclusive or. If we leave off exclusive, it means inclusive. And exclusive or means one or the other, but not both. So true exclusive or true is false, because it can't be both. And so this one and this one can't both be true. But true exclusive or false is true, false exclusive or true is true, and false exclusive or false is false, because it's neither. So the only time we get true is if it's one or the other, but it's not both of them. And a useful tool for writing out all this information instead of in a line, because this isn't the most clear way to view this, perhaps, is to use something called a truth table. So truth tables are used to make these sort of things a little more clear. The way to make a truth table, it's kind of like an addition table or a multiplication table. So if you remember learning sums, you would write down the numbers maybe like 1 through 10 or 1 through 12 in a column, and then write them across in a row, and then look at all possible combinations, which gives you some snapshot of what addition looks like, right? It tells you, at least for small numbers, what addition looks like, and then you do this for multiplication, and I spent a lot of time as a kid filling out multiplication and addition tables. Here it's a lot easier because we can actually write out the table for the entire space, since there's not an infinite number of things that we need to fill in. And we usually write them as columns. So let's look at the truth table for negation. Here's P, and this is the column of all the values that P could be. P can be true or false. And then true, if I negate that to not P, that's false. And if I negate false, that becomes true. So this is the truth table for negation right here. Then if we look at the conjunction, so we have P, Q, and P and Q, that's this here. Again, we write down all combinations of P and Q in the first two columns. So in this column and this column, we have true and true, true and false, false and true, or false and false. That's all combinations of values for P and Q. Then we take the conjunction in the last row. So if we take, for example, the second row, we have true, false, false. So this means that if P is true and Q is false, then P and Q is false. And looking across each row, that's what they mean. So the only one that's true in the third column is this first row, because true and true gives you true. Then everything else is false, false, false. The truth table for inclusive or for or in general, since we're going to start needing to get used to using or as inclusive or, could be written here. So this is always true as long as one of them is true. So in the first row, P is true and Q is true, therefore P or Q is true. Secondly, P is true, Q is false, therefore true or false is true, and so on. So we write down each value, and the only one that is false is the last one. So if they're both false, then neither of them are true, so P or Q is still false. And the last table is the exclusive OR table, which is just like the OR table, except for in the first row, you can't have both. So true and true, true exclusive OR true is false. So we will be making use of these truth tables to actually verify computations in this logic space. And I'll see you guys there in the next lesson.